Alright guys, and welcome back to NaN to GAN. Today we're going to be running through a little piece of code that I've written up as an exercise for us. Today we will be going through the MNIST dataset. So this dataset contains many thousands of handwritten digits and labels for them. So today I've written up this code here, and I'm going to run through it layer by layer with you guys. So an important prerequisite will be to install Keras, and then once you've got that, you're ready to go with this. So the first step is to import all of the things that we're going to need for our model today. So I have here the dense layer. The dense layer is pretty much just perceptrons, one down, one after another. It's exactly as I had shown on the board during the video, and the reshape is just to take an image and shape it back into just a bunch of perceptrons. We will be working with a sequential model. Basically all that means is that the model goes one layer after another, whereas in other models that we might be building, then we will have to have different models that have different outputs and different inputs. This one we just simplify it to say we have one input, one output, and all inputs just lead directly to the output. You don't have to worry about that too much yet. We are going to need a utility to categorical, so that just takes a number between 1 and 10, or any number pretty much, and makes an array out of it, where the only number that is a 1 is in that index, and then all the other numbers are 0. And then we will need the stochastic gradient descent optimizer, so that's what SGD is. Before we get working on our model, we have to obtain the data. So what this does is we are importing the MNIST dataset directly from the Keras library, and then we are putting into these two variables. We will not use xtest and ytest, but we will use xtrain and ytrain. And if you'd like to find out more about how to load in data and datasets and that sort of thing, I'd check out the Keras documentation for that, because they have a couple of datasets that you can use. And then our ytrain, we're going to make it categorical. So like I said, we're going to take it from being numbers between 0 and 10 to then we want arrays which have just one value being 1, which would represent our class labels. So now we'll want to get into actually building our model. So first we will define that this is a sequential model. We will add the first layer, which is a reshape layer, so that way we can go from a 28 by 28 image of the handwritten digits to 784 input numbers. After this, we're going to add 8 perceptrons, which are going to be all ReLU activated perceptrons, and then after which we are adding in 10 with a sigmoid function. Now the sigmoid function, which I will display on the screen right now, is a function to push every number between 0 and 1. Last but not least, we're going to want to compile the model. Our learning rate is how big are the steps that we are taking. So in the analogy of going down the valley, then our learning rate would be how wide are our steps? How far are we stepping? Our batch size determines exactly how many pieces of input and output we are looking at and trying to predict between each step. And epochs is a fancy word for how many times are we going through our data set. And then we'll want to compile our model with this function. We'll set our optimizer as stochastic gradient descent, we'll set our learning rate, and we will set the loss as mean squared error, as we saw in the video. And then finally, we will want to fit our model. So model.fit trains the model on first the inputs, then the outputs. It asks us how many times do we want to go through the data set and how big are our batches. So now that we've got all that set up, we can go into our command line and we can type in python main.py and we will run this, and it will run and train our model. So as you can see, the loss function, the loss value, is going down. So that is the distance between what labels we want to see and the labels that we're actually getting. As that goes down, that means the accuracy of our model is going up. And right here, we're about to reach 10 epochs, so our model will be completely finished training. So the average the average cost at the end of training is 0.16. So for each number, they're about 0.16 off. If we run it again, we can even change some of the parameters here. So what happens if we were to, say, give 32 perceptrons in the middle layer instead of 8? Would it affect our model at all? Well, let's try it. So as you can see, changing it from 8 perceptrons to 32 perceptrons greatly increased our accuracy. Our loss values are now approximately 0.075 rather than 0.16. You've almost doubled your accuracy, or cut in half your loss function. So what happens if we increase the batch size? Will it make any difference? Let's try that one. So while it did improve the loss, it did not improve it by very much. It can be affected this way, but typically batch sizes after 32 aren't going to make too much of a difference. So if we change what our learning rate is, what will happen? So let's change it up from 0.01 to 0.5. So as you can see, our loss value went up significantly as an entire 0.01 value. The reason for this is because if we go back to the analogy of descending into a valley, you would be taking leaps and bounds instead of just, say, a step. And instead of taking a step, you decided to take a leap and bound, so you might have missed where before it was a slope that was going down, but now you've overshot it, right? So you might not get to the exact bottom of it because you might just be bouncing around over top of the lowest point. This is even worse if we lower our batch size to, say, something at like 4. So let's see the effect of this. So now that we've finished training, you can clearly see that taking big, gigantic steps over highly inaccurate data like stuff with a batch size of 4 is not going to give us any good room to train. Therefore, our loss is significantly higher, nearly 3 times the amount as we had in our best run so far. So you might be saying, what happens if we add yet another layer? So let's try this. Let's try to add one more layer and change our learning rate and batch size back to their original amounts. And let's see what happens. So as you can see, the loss didn't really change that much, but shouldn't it change somewhat just because we're adding more stuff? We're adding more layers to it? Well, the answer is kind of complicated and it depends on your data. I think one of the reasons why it didn't get better is because of this example. Let me show you this really quick. Once we've increased the number of layers significantly, almost arbitrarily, we'll realize that the layer becomes too deep and there needs to be way too many layers of understanding between where the input is coming from and where the output is. So then it needs to push these numbers through 8 or 9 layers, in which case it just doesn't have that much information to give it. And the backpropagation loses a little bit of its influence each time it goes back through the layers. So therefore, trying to connect up the output and the input is going to be very difficult for your neural network. As we can see here, we have way more layers, so we should have way more understanding, but unfortunately that doesn't really help because we still have a loss that's nearly 3 times as much as we had in our best run. Other than that, those are the main concepts that I wanted you guys to get from this exercise. And so I'll leave it to you guys. You have the code, you have everything you need, and you can go ahead and try to change some values and explore exactly how these things work.